Hi, my name is Caden Smith. This is my first lab for Physics 2211. The purpose of this lab is to explore the laws of motion put forth by Sir Isaac Newton, including the Newton's second law, which is equivalent to the momentum principle, stating that objects maintain their current momentum unless acted upon by an outside force. These laws are only true under ideal conditions in which forces of friction are negligible. In this scenario, a point mass would move with a constant velocity in a straight line for an infinite amount of time. In this lab, we will directly compare the motion of our experimental model and its theoretical counterpart, as well as see why the results show an acceleration acting on our system in the experimental model. In this scenario, the system is the ball and the surroundings is everything else in the universe, including the earth, carpet, and the air. Some relevant formulas for this experiment are the momentum principle and Newton's second law, which are connected to one another, and then the position update formula shown on the top right of the screen with the code below it, and the velocity update formula on the bottom right hand side of the screen. The velocity update formula is similar to the one shown, but A would be replaced by force over mass. The initial conditions for this experiment are both in the experimental and theoretical models. The initial velocity is 2.665 meters per second, which was calculated via the tracker data shown on the top left of the screen. The theoretical net force applied is 0 newtons, as shown here with the code here, and the initial time used was 0.5 seconds, with the final being 2 seconds. The time intervals vary slightly for this experiment, and there's information about the tennis ball on the right, including its mass, diameter, and circumference. Shown here is the glow script code for our theoretical model in this experiment. What's highlighted now is the visualization, including the object, trail, and origin, which will be shown once we run this program. The graphing is shown below it and how it works, including a position versus time graph, as shown here, and a velocity versus time graph, as shown here. The initial conditions are coded in, as shown here, including the ball position using the vector 0, 0, 0, and the ball velocity using the vector 2.665, as discussed earlier, 0, 0. The net force is also shown here using the vector 0, 0, 0 to represent no net force acting upon the object. Below is the velocity formula for the object, as shown here. It's very similar to the velocity update formula we showed earlier, just in a form that Python can read. Same is true for our ball position formula. Now we can go ahead and run this program. There it goes, straight off to the right. Camera zooms out so you can keep seeing it. Below we have our position versus time graph. As shown now, the slope here, as I'm illustrating with the mouse, represents the velocity as shown in this graph. Finally, at the bottom, we have the data of position versus time and how we got to the velocity. Now we will show the video from our experimental model. There's the tennis ball and it goes. Each click represents a data point being tracked in tracker. Here it is the second time. Shown here is a ton of the data from our experimental and theoretical models. It will be graphed in just a moment. First, we have our position versus time graph, the red being the theoretical line. It is perfectly linear as it follows a theory. In the experimental model, it starts off just as quick, but the position falls behind. In this graph, it shows the velocity. The theoretical velocity remains constant and unchanged, while the experimental velocity varies because of the tracker information and drops slightly. The experimental model is very similar to the theoretical model in this experiment with an almost constant velocity. As expected, the experimental model, the tennis ball gradually slowed down because of the force of friction as calculated on the right. There were two main possible sources of error in this lab. First of which, as seen on the right, the velocity of the tennis ball was scattered and loosely followed the trend downward in our experimental model, and this variation is because of limitations involved with the tracker software. Secondly, the ball's distance from the camera was not exactly equal at all times, leading to more scattering at the edges of our graph. This experiment, if the axes were flipped, the position graph would be mirrored along with the velocity graph, both becoming negative. It's impossible to tell how many forces are acting upon the ball in this experiment, as there's an infinite number, because technically everything affects the forces on one another. And in conclusion, the momentum principle is applicable to the real world with slight errors to do with friction and unseen forces.